Well, good morning. This is 9:31 in the morning on the Wednesday, the 12th of April, 2017. It's supposed to be Math 125, Calculus 1, and right now I'm the only one in the classroom. This is how my linear algebra class started this morning, too. This is becoming a bit of a habit here, it seems. So we're going to get started with this. I'll wait until the student comes in to make any announcements, just because, well, no, let me go and make them now in case someone's not here and they're just listening at the first of the class. Office hours today and everything today should be about normal. I hope so anyway. I'm not feeling very well, but as far as I know, I'll be in class pretty much from now until 3:15, but at 3:15 I'll have 2 hours of office hours from 3:15 to 5:15, and then probably I'll stay a little bit later than that today, just to take care of some stuff. I'm way behind in grading right now because we've been working on budgets for next year. I turned all that in last night. That's one reason I'm not feeling too well. I was here until between 9:15 and 9:30 last night. And we have a student coming in, I hope. Yes, we do. All right. It's so good to see you. I hate talking to myself. It makes me feel like I'm a little missing it. Okay.
You guys had class this morning?
What's that?
Yeah, what's that?
Yeah, right. Uh-huh.
It's storm.
Yeah, no, the whole school is closed. Yeah, so. All right, let me get here. I was just making the... Last Wednesday we were out, yeah. That was when the storm was. And that now put us a week and a half behind because they started class on a Tuesday, so we lost the Monday of the first week of class. And then we had Martin Luther King Day that put us 2 days behind, Tuesday, Thursday classes, and then we missed Wednesday of last week because of the storm. So that puts us a week and a half behind. The other Cal 1 class is on the Birmingham campus is a Tuesday, Thursday class, and they're ahead of us, but I don't care. I mean, we're fine. Okay, I was just going over, the rest of this week is kind of screwy as far as office hours go. Today's pretty normal, whatever normal is. I was just explaining this before you came in case anyone was listening here. This week started wacko to me anyway, and it's just gotten stranger as it's gone on. I'm not feeling all that well today, mostly because I was here till about 9:15 or 9:30 last night working on budget stuff, and I got that turned in last night. But by the time I got home, it was after 10, and by the time I finished eating and got things taken care of at home, it was after 11, and so I was after 11:15 or 11:30 or so before I got to bed, which is late for me. And then I got up at 5:15 this morning, so not running too well, and I haven't been feeling well today anyway. And all week I've been behind in sleep and gotten worse and worse every day, so if I'm not with it too much, that's why. Okay, but today, as long as things go okay, I'll be here. I'll be in class pretty much until 3:15, but I have my normal office hours 3:15 to 5:15. But tomorrow is different because we have honors and awards in the morning on the Birmingham campus. So I'll be here at 7:45. I'll teach my first class. That's 8. And I'll probably end it between 9 and 9:15 because I'm supposed to head over to the Birmingham campus and be ready for honors and awards. So since it starts at 10, they want us there by 9:30. I'm not super anxious to be there by 9:30 because we just stand around for a half hour with absolutely nothing to do. And so I'll be between 9 and 9:15. Ending the class, then I'll head over to Birmingham, get there between 9:30 and 9:45, have plenty of time to get ready for the honors and awards, and then we will be in there. That's going to go, they say 10 till 12. Seldom do they finish on time because basically seldom do they start on time, and then they do a lot of talking in between. So anyway, I won't be back on this campus any earlier, I don't think, than 12:30. So my office hours normally on Tuesday and Thursday are from 10:45 to 1:15. Tomorrow it's going to be 12:30 or later until 1:15. Okay, then I got my afternoon class, and that's all afternoon, 1:15 till 5:45. And then on Friday, I'm usually on the Birmingham campus, 7:45 to 1. Not this Friday. I've got an infusion Friday, and that goes from, it starts at 8, but I have to be there by 7:45, and it usually goes at least till 4:30. So not going to be on Birmingham campus at all on Friday. So limited office hours tomorrow, no office hours on Friday. But then next week should be a fairly normal week. Of course, got to finish taxes this weekend too, so that's going to be another headache, but that's outside of class. Okay. Any questions then? I did want to say this now that you're in here. If you were wanting to apply for one of the academic scholarships here at Lawson, that deadline is next Monday. So if it's for any time, but yeah, especially they do it right now for summer, basically.
Where's the packet for?
I'm sorry?
Where's the form at for?
I've run out of mine, but they have plenty of them down in the financial services office.
Where's that?
It's if you go out the door here, say again.
Once I leave today, I don't have time to go grab it.
Okay. If you go out the door here into the hall, go down this half flight of stairs right there, go past the restrooms, go across that corridor. When you get to the view part right there, you're looking in financial services. So there's a door here, there's a door there. All right, I'll continue with, let's go on and get started on the calculus. We've spent enough time talking about preliminaries. Okay, we are recording. Let's get the slideshow set up for the current slide. And we're beginning 4.2 today. Okay. All right. Now, 4.2 is talking about extreme values, okay? In many applications, it's important to find minimum or maximum values of a function of f, your function f. For example, a physician needs to know when the maximum drug concentration in a patient's bloodstream when the blood is administered. This amounts to finding the highest point on the graph of C, this picture here, which is the concentration in the blood at any time t. That's this figure. We refer to the maximum or minimum values, max or min for short, as extreme values or extrema. Now, that seems like a strange word, but maximum is a Greek word, and the plural in Greek is a, like alumnus, alumna, singular plural, okay? So a maximum would be two maxima. If you have more than one maximum, it would be a maxima. More than one minimum would be a minima, and more than one extreme value would be an extrema, okay? Even though extreme probably isn't a Greek word, it may be, I don't know, but it's usually not used as a noun, but since we did plural with a MA on the other two, we'll do it on this one too. Okay. And the process of finding them is called optimization. Okay. Sometimes we're interested in finding the minimum or maximum of X, in particular interval I, rather than over an entire domain. So we'll take a look at that too. But let's look at this figure first. And this is not unrealistic. This is pretty much what goes on. If someone were to take a pill, for instance, tomorrow or Friday when I'm having the infusion, one of the first things they do is give me 2 Tylenol, okay? Now, they're supposed to, I found this out yesterday when I was at my doctor's appointment, 3 out of the 4 times I've had this new drug, which I started either back in December or November or sometime. It's been every 2 months since, I've gotten real hot, a little itchy, and broken out in a rash. Not a big deal, but it's just uncomfortable. And I had been telling the doctor that, but he hadn't really paid lots of attention to it, I guess, until yesterday. He said, "You've been having some problems with this." I said, "Well, yeah, I've been right here." So I guess maybe the nurse that I had last time, who was really, really a good nurse, maybe she wrote it up so he saw it, And so he started asking me questions about it, and he asked how long did they wait before they administered the drug after, they had given me the stuff ahead of time. Well, I said, well, I never know exactly when they're doing what in what order. I just know they ask for my name and birth date, and then they start giving me something. So I said I didn't know, but I said usually the rash comes out about midway through the procedure, then they shut it down or slow it down or stop it for a while and give me something else and then pick it up again. One time they forgot to do that, and I didn't get a full dose. So anyway, I'll take 2 Tylenol to begin with, and if you'll notice here, and this is probably not that unusual, okay? You take it, and of course, at the time you take it, you have nothing in your bloodstream. You take it, and it dissolves in your stomach pretty quickly and gets out into the bloodstream at a pretty fast rate, but at some point, then you get the maximum value, and notice there, at that maximum value, the rate has been increasing, and still it reaches 0. That's the rate. Still getting it in there, but the rate is approaching 0, and then the rate is going down. Still giving stuff into the blood, but this is the drug concentration in the bloodstream as a function of time. And they say, see example 74 at the end of the chapter, and you can look at this further. But what I was saying, this is probably not an unusual thing, because that maximum here appears to be pretty close, maybe a little before 2 hours. Well, if you think about it, most of these, a lot of drugs, they'll say take 1 or 2 every 4 hours, okay? That would make sense here, because about the time this starts going down, take another one, and then if it follows the same path, and goes up here, and then another 4 hours here, you have not exactly an even dosage in your blood, but it's pretty consistent. You have little maxes and mins, but overall it's pretty consistent. Okay? Well, my story was, and the doctor asked about this, he went and started looking into it. Now, this has been going on for several months now. He finally noticed they had not allowed, it's supposed to be, I guess, sort of standard protocol. You give the stuff ahead of time, like the Tylenol, the Benadryl, and the 2 steroids, and wait at least a half hour before you start administering the drug. And he said he looked at the times, they were 7 minutes, 9 minutes, 12 minutes. The only time they waited the full 30 minutes was the one time I didn't have any reaction. He said that was the problem. Not that I'm having reactions, it's just they weren't administering. They were starting the infusion too fast, too soon, not giving the other drugs time to get into the bloodstream and start doing their thing. Now, 3 of those are being done intravenously, so therefore you don't have to wait 2 hours. It was only about a half hour. Okay, so anyway, that's a realistic type situation there. So with that in mind, let's move on to the definition of extreme values. We've just talked about them. This gives it a little more formally. Okay, definition, a little bit more formal terms. Let f of x be some function on some interval I. Doesn't have to be over the entire domain. Let f be some function, be a function on some interval I, and let a be a value of x in that interval. Okay? Then we say that f of a, which will be the functional value at that value a, is an absolute minimum of f of x on that interval I if f of a is always less than or equal to all the other f values, the y values, the f of x, for all other x's in that interval. It's an absolute maximum if that of f of x on I, if f of a is always greater than or equal to any of the other f values or y values on that interval I, x and I. Okay? Now, as they say at the bottom of the page, in the left-hand column underneath figure 1, often we drop the term absolute and speak simply of the minimum or maximum or min or max. And if we don't mention an interval, it's understood you're referring to the entire domain of the function. So not always do we say absolute, and not always do we specify an interval. Okay. Now, does every function have a max or a minimum value? And they say clearly not. Okay. I'm not sure it's all that clear, but we'll try to make it clear. So let's take f of x equal x, which is your identity function. Okay. F of x is equal to x, increases without bound as x goes to positive infinity, decreases without bound as x goes to negative infinity. In fact, the extreme values do not always exist, even if we restrict ourselves to an interval I. That one you would, okay? But you have another sort of strange situations, and all these will be a bit on the strange side. Here's some examples. The first is if you have a discontinuity, okay? Let me go on and blow this up. See if I can get it all on one. Yes, easily, I think. Okay? The first one, we have a discontinuity. F of x is this function here. Looks like it might be some sort of an absolute value type deal, though we don't have enough to tell that for sure. It's defined from A to B, including the A and B. But it has a discontinuity at C, whereas you would expect that to be somewhere around 3. It's actually down here at 2. Well, that's a discontinuity. So therefore, this function doesn't have a absolute maximum value anywhere on that function. Okay, you might say, well, is it 3 pretty close to an absolute? Yeah, it's pretty close, but it's not absolute. Okay? I'm assuming that is value 3. The function isn't defined, doesn't have a value of 3 there. It has a value of 2 there, okay? So, just before that, it's approaching 3, but never gets there. Just past that, it's leaving 3, but never at 3. So you can't find any value for f, okay? F of c is definitely not the absolute maximum, because either one of those would be, but you can't find the value anywhere there. Say c minus h or c plus h, no matter how big or small you get h to be, there's always another value closer to c that it would be a larger f value there. So that would not have an absolute maximum. Would have an absolute minimum at a, because that would be 1 there. At b over here, it looks like it's about 1.5, so that wouldn't be. So a would be an absolute minimum. The value would be 1, doesn't have an absolute maximum. Okay? Now, this next one is a function that's not defined at A. It's a continuous function with no max or min, no minimum or maximum, on the open interval from A to B. Okay? Open interval at A, it doesn't have a value because it's open interval. It's not even defined there. Okay? But anywhere past A, it has a value that's increasing until you get close to B, and then it's going to positive infinity, which doesn't have a value at B either. Okay? And if it's not defined at A or B, and as you get closer and closer to B, it gets greater and greater. As you get closer and closer to A, it gets lesser and lesser, but not nearly as fast. It's approaching 10, but never reaches 10 as X approaches A. There is a limit there, but it never reaches that limit. At B, as you get closer and closer to B, there is no limit. It gets infinitely large. So that would have neither an absolute maximum or an absolute minimum or an absolute maximum. Okay? Now, this third function here, and this happens to be a continuous function on a closed interval. See, this was a closed interval in the A part. It was an open interval in B. It's a closed interval in C. So if you have a closed interval, it still doesn't guarantee you're going to have an absolute maximum or minimum, but it could come closer. Open intervals, you lose the endpoints, okay, that could be a maximum min, like A was here back in A. X equal A was a minimum there. It would have been if this was a closed interval here, at least on the left-hand side, that could have been an absolute minimum, but it wasn't because it's a open interval there, okay? But then on this one, continuous functions on a closed interval has both a minimum and a maximum on that closed interval, okay? In this case, the minimum is over here somewhere between A and B. At A, that's neither a minimum nor a maximum, but at B, that happens to be a maximum. It doesn't have to be at an endpoint. In this case, it just happens to be. So the minimum, absolute minimum, is somewhere between A and B, a little bit closer to B, and the absolute maximum of H of X would be at B. Okay? So every continuous function on a closed interval, A to B, has both a maximum, minimum, and a maximum on that closed interval. Maybe one of the two endpoints, either maximum or min, or not. It doesn't have to be, but it's going to be, it will have an absolute maximum. See, this is not a continuous function in A, and in B, it's a continuous function, but it's on an open interval. So, the open interval may wipe out the possibility of absolute maximum or minimum. Having a discontinuity may wipe out either a maximum or minimum, but having a continuous function on a closed interval guarantees you both a max and a min. And if you go back to their first example, the identity function, I'll have to get out of that to draw it. Let me get my pen activated here. Let's just say, just for argument's sake, it's not. Okay. Let's do maybe here. Let's do the identity function here. If that was your identity function. But if it's defined, say, from A to B, so the function continues without bound, but if you talk about it over a closed interval from A to B, then the absolute minimum's at A and the absolute maximum's at B. Okay? If that was an open interval, it wouldn't have either a max or a min. And if it's from positive to negative infinity, which is an open interval, it has no max or min. It keeps increasing to the right, decreasing to the left. Okay, so here's our theorem 1. Okay. I'm hoping not to have to, but I'm feeling like I might have to go get something to drink. I'm not throat is closing up on me, and it's also hurting a little bit. I have a feeling it has to do with pollen, but I don't know that either. All right, here's theorem 1. Existence of extrema on a closed interval. Basically formalizes what we just said. A continuous function, that was a requirement. You can't have discontinuities and guarantee this will happen, but if you have a continuous function f of x on a closed, which is a bounded interval I, which it's evaluated at A and at B, and those values count, it takes on both a minimum and a maximum value on I. Minimum and maximum values could be at the endpoints or not. Either one of them, it doesn't have to be. Okay. Now there is a reminder over here, a closed bounded interval I on A to B, endpoints included, where A and B are both finite. We often drop the word bounded and refer to I simply as a closed interval. Okay? An open interval A to B, endpoints not included, may have one or two infinite endpoints. Okay? So if we say it's closed, that implies it's also bounded. That you don't have anything going to infinity. Okay, here's a conceptual insight then. Why does theorem 1 require a closed interval? Think of the graph of a continuous function as a string. If the interval excuse me, my throat's hurting. If the interval is closed, sorry, the string is pinned down at the two endpoints and cannot fly off to infinity or approach max min without reaching it. And your 2 B, oh, that was the figure there that I have marked up. Let me take the marks off. Just happened to use that one. Okay, that's a open interval. One end is bounded, the other one is not. Okay. Intuitively, that it must have a must have a highest and a lowest point if it's closed. If it's not closed, it doesn't have to. Okay. However, a rigorous proof of theorem 1 relies on completeness property of real numbers, and they say see Appendix D if you're interested in pursuing that. So, with that in mind, now let's give a definition for a local extrema. Okay? Sorry, my hand is not operating well. Okay. Using the wrong keys here. I think I'm going to have to go get something. I got to clear my head. It's getting harder and harder to breathe. I don't know where that came from. Yeah, here's local extrema. Okay, so I'm going to pause it for just a moment. Sorry. All right, sorry about that. My throat was clogging up and I just could hardly talk. I still can't talk well, but it's a little better than it was. So let's pick up where we left off. This is local extrema, the definition that's on the bottom of page 201 in the current edition. I don't know if any of you have the older edition, and one of the students in my Cal 3 class has the older edition. So here's your definition of local extrema. We say that f of x, some function of x, has a local minimum, not absolute extreme. Those are your absolute minimum and maximum. These are local extrema. We say that f of x has a local minimum at x equals c if the function at that value, x equals c, so f of c, is a minimum value of f on some open interval in the domain of f that contains c. A local maximum at x equals c if f of c is the maximum value of f of x on some open interval in the domain of f that contains c. Now that's a lot of blah 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 words. They have a little blurb on the side, which I guess is pretty good. When we get to the top of the hill in an otherwise flat region, our altitude is at a local maximum if you're at the very top. But we're still very far from the point of absolute maximum altitude, which is located at the peak of Mount Everest. And that's why the difference between a local and an absolute extreme value, extrema. Okay? So, let's see. Hopefully they've got some figures coming up. Yeah, here's some. Classic kind of figures for this. Okay. Here we have a function, the red line here in A. Okay. There's a function. Looks like the same function you have in B, but let's just focus on A now. At A, now notice they don't have an interval defined. You're assuming it's all real numbers. If indeed that's the case, and this is going up without bound here, and up without bound there, then this is an open interval. So you're not guaranteed to have an absolute maximum or minimum. But in this case, we happen to have an absolute minimum if that were the case. This is a local minimum because of all the values around this value. Let's call this one A. Okay? All the values around x equal A, the f of A is the least value less than or equal to all those other, so that is a local minimum. And in this graph, if we can believe it, it may also be an absolute minimum. Not guaranteed to have one, but in this case you do have one. Right here at C, this appears to be a local maximum because in the domain around x equals c, not too far away from it, then that is by all means the largest value. Okay, so that's a local maximum. Down here, let's call this one D, say, down here. At x equal D, f of D is the lowest value for any values close around x equal D. Okay? See, if you get too much further away, like over here, now you have values less than the f of x. Okay, f of D. But any time the x is fairly close to D, then that is a local minimum. All right. Now, if, however, I shouldn't have used the letters I did because I wasn't looking ahead. If we close the interval here, not have it go on forever, and you have a closed interval from A to B, then this would then become an absolute maximum on that closed interval. You're guaranteed to have one. Okay? Now, we don't call it a local maximum because the x's can't be on either side of that. The x's are only required to be on the right-hand side of A, okay, because that is the endpoint. This is now an absolute minimum on that interval. It's a local minimum on that interval. This is a local max here, but not an absolute max because there's your absolute max over there. Here's another local minimum here, not an absolute because the absolute minimum's over there. And then B ends it, and that would be, you might call it a local maximum, but generally we don't because the x can't be on either side of B. It only can be on the left-hand side of B. So, usually your local max and local mins are interior points. They can't be, or usually we don't let them be, the endpoint. Your absolute max surely can be an endpoint. Okay, it doesn't have to be, as in this case, the endpoint here is not a local max or local min. It's not an extreme value. Okay. Now, the question then comes, how do you find these local extrema? Crucial observation is that the tangent line at a local minimum or maximum is always horizontal. In other words, if f of c is a local minimum or maximum, then f prime of c must be equal to 0. However, this assumes that f is differentiable, which you have to have that as the case. Otherwise, the tangent line may not exist. And they show this in the next couple of figures. So let's go back. The very next figure looks a lot like the one we're just looking at. Sorry. I thought I had cleared out, but obviously it's not staying clear. All right, the A one here, that looks a lot like the one we were talking before. It's blue now rather than red, but it looks a lot like that same function. Okay? Your local extrema, okay? Remember I said you usually don't count those as endpoints, and here's the other reason. Because your tangent lines at endpoints typically aren't 0 or horizontal, slope of 0. So these three, local min, local max, local min, this happens to also be an absolute max. It doesn't have to be. All it required for it to be a local extrema, either maximum or minimum. Okay, let me get rearranged again. I had to take a break just to clear my head. I'm having so much drainage. I don't know if that's because it could be pollen, it could be change of weather. I don't know, to be honest, anything. I'm really dragging today. You got one of the forms?
I did.
Okay.
I had to get a layer of recommendation.
Right. Okay, now, be sure, don't put off that until Monday, because that puts a lot on somebody to have to get it done that day. Be sure to ask them to do it. What's that?
It should be done by Friday.
Okay. Yeah. Okay. All right. So here's what we're talking about. We're on page 202. This is figure 4. And we're talking about local extrema. Absolute extrema, as in absolute max and absolute min, they could be endpoints. Your local extrema, we usually restrict that to be interior points, and they are on a continuous function, smooth continuous function. Those are going to be the places where your tangent line is horizontal. Because it's a smooth function, and it's a decreasing function here, decreasing. That means it has a negative slope on the tangent line. But then when it stops decreasing and at the point where it starts increasing again, the tangent line is negative, and then later it's positive. That means somewhere in between there, if it's a smooth continuous function, the tangent line had to reach a slope of 0. Slope had to reach 0. That identifies your local extreme. Same thing here. Local maximum there. This was a local minimum. Happen if this is a true representation of the curve, that was an absolute extreme. That's fine, but it is a local at the same time. your local maximum, your slope was increasing, meaning positive, 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 started getting slightly less positive, and after a while it became negative. But if it's a smooth, continuous function, that meant somewhere in between there, the slope had to reach zero. That's your local maximum. Okay? Same thing down here, the slope was negative, 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 all the way down. But then somewhere later it's positive, and if it's a smooth, continuous function, that means somewhere in between those two values, that it was last negative and then became positive, there had to be a point where that slope was zero. So the tangent line is horizontal at the local extreme. Now, you can have a local minimum, a local extremum, that occurs at a point where the function is not differentiable. See, this function is differentiable everywhere. This one is not, because coming down here you have a negative slope, negative slope, negative slope. Suddenly it becomes positive, and nowhere in between there did it ever reach zero. That means you have a discontinuous derivative there. The function is not differentiable at the point C. Okay. Can't think if there would be anything else. By the way, this point here is called a cusp. Okay, where it comes down to a point. You could have a point that's not a cusp, like an absolute value. That would not be, it's a local minimum, but the function is not continuous there either. That's called a, well, some books call it a corner or something like that, where you have different slopes on either side. Here, is not even differentiable from either viewpoint. Okay. Now, here's another definition. Lots of definitions in this section. We will ultimately get to doing some problems, but right now they're still defining a lot of things. Man. I'm so sorry. I'm feeling so lousy. Here's another definition. Critical points. A number C, and you almost wonder if that's why they chose the number C to represent critical points. It's used pretty consistently that way. A number C in the domain of F is called a critical point if either of these two situations occur. Either the first derivative of the function at that value C is equal to zero, that means a horizontal tangent line, or if f prime of C, the first derivative of that function at that point C, doesn't exist at all. So let's go back a slide, and that would make all three of these critical points, and this one a critical point. Now they didn't mention it, but these two up here would be critical points as well, because your horizontal, your slope of your derivative is zero here, here, not defined here. It looks like you may be coming up on another critical point somewhere over here. This one looks like it's heading south, and it's staying south. This one's bending as if it might actually have another critical point. But in that portion of the domain, you have three critical points, where the derivative is zero, where the derivative is not defined, and where the derivative is zero. In this case, the derivative is zero, derivative is zero, derivative is zero. Okay? So those are what your critical points are. The places where either the first derivative is equal to zero, or the first derivative is not defined. Okay? Finally here, we're ready for example 1. This may be example 1. I think it is. Find the critical points of this function, f of x is equal to x cubed minus 9x squared plus 24x minus 10. Okay? All right. It says find the critical points. Okay? What is the definition of a critical point? What's that? I'm sorry. What is it? What is it?
When the domain equals zero or it don't exist.
Okay. That is where the first derivative is either 0 or doesn't exist. That's what a critical point is. Now, on some domain, yeah, it's within a domain, but the definition of the critical point is the values where either the first derivative is 0 or the first derivative doesn't exist. So what's the first thing we got to do to determine a critical point? All right, some areas here. Okay. So if my X chromosomes made it today, where are the Y's, huh? All right, we're on in chapter 4, section 4.2, and we're on example 1, bottom half of page 202 if you've got the current text. All right, and here's the function. F of x equal x cubed minus 9x squared plus 24x minus 10. The question here is find the critical points. Find the critical points. What's the first thing you got to do to find the critical points? Yes, take a derivative. So the first thing we do is f prime of x. And what would that be? 3x squared. That's a 24, right? Done. There's your first derivative. What do we do? Either set it equal to 0 or determine where it doesn't exist. Now, hint. This is a polynomial function. Polynomials are continuous and smooth. The derivatives exist everywhere. Okay? The domain is all real numbers. There's no problems anywhere. So the derivatives also are defined everywhere. So here, there's not going to be none where it doesn't exist, but we might try to find where it's equal to 0. How would you solve that equation then? Okay, a little bit louder. Factor out of 3, is that what you're saying? Yes, let's do that. 3 times x squared minus 6x plus 8, and that has to equal 0. Say that one. Is 3, is that what you said?
I'm saying, okay, after that you would do like,
Unfoil it, right? Okay. Yeah, let's do that. Only possible factorization for x squared would be x times x, right? Yeah. And then you have to have a minus and a minus because that sign is positive. That means these two signs have to be the same. Because the middle sign is negative, that means both of those have to be negative. And then as you just noted, 2 and 4 will work. Okay. Now, what do we do then? Factor 3? Okay. Except 3 can never be 0. So divide that out. Who cares about 3? But set the other 2 equal to 0. So x minus 2 equals 0. What would that yield? X equal 2. And if you set x minus 4 equals 0, that's x equal 8. Right? No, I'm sorry, 4. I can't read my writing. Okay. Goodness gracious. Let me clean that up a little bit. That's a 4. Okay. I don't, yeah, I can't read, I don't, say again? No, it wouldn't because 3 can't equal 0. You set each factor. See, what you do with 3 is divide it away, okay? And x minus 4 equals 0, add 4 to both sides, and you get x equal 4. So those are your 2 critical points, okay? X equal 3, in fact, x is is not equal to 3. If x is equal to 3, then you would have something like 3 minus 2 and 4 minus, 3 minus 4, that would be a 1 times a minus 1. Yeah, that would be, that would be a minus 1. Times 3 would be a minus 3, and minus 3 is not equal to 0. So, no. The 3 is just a factor without a variable in it, so you can divide it out. Okay? Those are your 2 critical points, or at least the x values of the critical points. Okay? To get a point, though, you need a coordinate pair. So you've only got the x values here. What we do to get the y value is plug it back into your original function. Okay? You weren't here to hear. I am really dragging today. I've got, my head hurts. I'm all clogged up. I didn't have much sleep last night. I had very little sleep on Sunday night. It's been a bad week so far, but so if I'm flaky, that's why I'm flaky. All right, what you do is plug this back in. F of 2 would be what? Yeah. 2 cubed minus 9 times 2 squared plus 24 times 2 minus 10. Okay? 2 cubed is 8 minus, what is 2 squared? 4. 9 times 4 is 36 plus 48 minus 10. Okay? I like to add the positives. That gives me 56. Add the negatives. That gives me 46. So that would be 56 minus 46 is 10. So our first point would be 210. Now this graph doesn't do anything on the y-axis. Let me clean up a little bit just so you can see. Okay. it doesn't put any scale there. It just shows you where those horizontal tangents are. It doesn't give you value. But now we know that when x is 2, this would be right here would be 10. Let's plug the other one in. Alpha 4. What would that be? What would that be? 4 cubed minus 9 times 4 squared plus 24 times 4 minus 10. Okay? You happen to know what 4 cubed is? 64 minus 9 times 16, right? Plus 24 times 4, 96 minus 10. Say that again. So you got a 64 minus 144 plus 96 minus 10. Man. Okay, add those two together, you get 160. Add these two together, you get 150. No, 154 minus 154. So that adds to be 6. So whereas this one was 10, this one is 6, that even looks reasonable. Okay? So actually the second point would be 4, 6. First point would be, the critical point would be 210. Second critical point would be 4, 6. Now we usually talk about it where x equal 2 and where x equal 4. We don't always evaluate it, but really a point is an ordered pair, okay? An x and a y value. See how the book did it. They just said where it's located, x equal 2, c equal 2, and c equal 4. But they don't give you actually the point. It says find the critical points. It seems like you need to get a point, not a value. Okay. Now, any questions on that? Okay. There's one of our favorite old functions of all time, right? The absolute value function. Okay? Now, what do you reckon the first thing we're going to do here? Second? Yes, let's take a derivative. But actually, that's a rather strange function, isn't it? It has one value over here and a different value here. So really, for absolute value, the best thing to do is to split this and make it one of our favorites, piecewise defined function. Oops. I'll have to get out of here and make this f of x equal, what is this side over here? What would be the function for this side on this side, on the left? What's that? That would be negative x. Let's see, I'm putting that in the wrong place. Alpha of x, no, I think that was right. That's how we usually do it, isn't it? Alpha of x is equal to negative x for x less than 0, and it's equal to, what is it over here? Positive x anytime x is greater than or equal to 0. Okay? So that is our function. The absolute value function, yeah, that's a way to show it, but actually before you can take a derivative, you have to define it in terms that we can do. So let's take the derivative of this then. F prime of x would then be what? Let's take first the derivative of that piece. That would be negative 1. And that would be anytime x is less than 0, and it is positive 1 anytime x is greater than or equal to 0. Okay? So you have two derivatives. And actually, I should be a little more careful here. I should be more careful here. I think that at x equals 0, we can't define the derivative, can we? Because the limit as you're coming in here is minus 1. The limit as you're going in there is plus 1. It doesn't have a limit. It doesn't have a derivative at x equals 0. So therefore, that's our critical point. This is never 0. That's never 0. So you're not going to have a critical point anywhere here or anywhere there. But at x equals 0, where the derivative does not exist, that's your critical point. So your critical point is x equals 0. And at x equals 0, f of x is also equal 0. So your critical point is the line 0, 0. That's your critical point. Okay? Because you plug in x equals 0 here, absolute value of 0 is 0. The derivative, though, you can't evaluate that at 0 because it's minus 1 here, plus 1 there. It has no value at 0. So here's a case where your critical point has the derivative that does not exist. And it exists everywhere else. All real x's that are less than 0 is minus 1. All real x's greater than 0 is positive 1. But at x equals 0, the limit doesn't exist. So the derivative doesn't exist. Okay, does that make sense? Now, goodness, my head hurts. And I'm having trouble getting my eyes to focus. I can't really see these lines well. I think I've got them good enough. I'm dragging. I may have to go get something else to drink for my throat. But here's Fermat's theorem on local extrema. Now, I'm going to take a moment here of encouragement, you might call it. This is, I think, my one and only class in which nobody has turned in a research paper at all. None. Okay? I have some other small classes, but actually one of those, one that met this morning, everybody's already turned in the research paper. And even in my mini-term class, one person has turned in the research paper. Okay? So let me, while I'm about to mention it, he would be a good topic for Mott. Okay? He's a famous mathematician. He actually wasn't a mathematician. He just played around at mathematics, okay? But he was one of the best math minds out there, okay? And he came up with this theorem. You can write on the theorem too. on local extrema is f of c is a local minimum or a local maximum. I'm sorry. Then C is a critical point of F. Okay? Well, we should have known that. A local minimum and local maximum was defined where the derivative is either 0 or undefined. So that makes sense. So here's his theorem on extrema. Then if it's a local minimum or local maximum, then C has to be a critical point of F. Now, we will hit this later, but there are some functions where the derivative, and for instance the cubic function, it comes up like this, levels off here, and then keeps going up. Its derivative there is 0, at 0. But that's neither a maximum or a minimum. It's a neither. Okay? But by our last definition, that now this is a number C in the domain. This is the definition of a critical point. Number C in the domain of F is called a critical point if either f prime of C is equal to 0 or f prime of C doesn't exist. That case, the cubic function, that is a critical point, but it's not a local maximum or minimum. Okay? Fermat's theorem says that if it's a local maximum or minimum, then it is a critical point, but it doesn't say those are the only critical points. That's the key. Okay? Not a big deal, but it is a deal. Okay. Sorry. And there is a proof to it. And this is part of the proof. This, by the way, is a difference quotient, which leads to a derivative, okay? And if this difference quotient is greater than or equal to 0, or h is greater than 0, if that difference quotient is equal to 0, there's a good chance that is going to be a local maximum or minimum, okay? The next part, you have to really look at the whole proof to do this. But if this is also true, that is that see, what we've left out here, what they've left out here, is the figure that's here, because all this is based on that figure. Okay? Let's see if they get the, yeah, here's the figure. Really, they put the equations before the figure, and they almost make no sense without it. Okay. What we had in the first case, or second case, was the secant line being the negative slope, and in the first case, the secant line was a positive slope. Less than or equal to 0, greater than or equal to 0. Now, if you have that case, that means somewhere in between there, you have to have a place where either that derivative is 0 or the derivative is not defined, because it's negative coming this way, positive going that way. Somewhere in there, it either was 0 or it's not defined. And in either case there, that would be a critical. In this case, if you are going from here to here, the secant line is negative, here to here, the secant line is positive. Somewhere in between there, it just happens to be at C, the tangent line is horizontal. So that would be, that's how they go about part of the process of proving this theorem. Now, the conceptual insight they have here yuck. I have these things so out of order. Let's see. Yeah. This is the conceptual insight. Okay? I think it's right next to it. Fermat's theorem does not claim that all critical points yield local extrema, but it does claim that if it's a local extrema, it's a critical point. But it doesn't mean that's all the critical points. And this is the example I was just giving you. In this case, this is a critical point because your first derivative is 0 here, but it's not a maximum and it's not a minimum. Okay? Alpha 0 is neither a local max or a local min. So all Fermat's theorem said, if it is a local max and a local min, then it is a critical point. But it doesn't mean it's exclusively that. Okay? This one can have a critical point where it has neither a local max or a local min. Okay? Now we back up and go to theorem 3. Sorry, I'm having to do this so weirdly. Whoever did their slides did not get them entered well. Goodness. I've only had something close to a migraine, I think, twice in my life. But yeah. I'm sorry? What about it? Oh, you need one. Okay, sure. I didn't realize you didn't have one. I think it's right here. Make sure that's, yeah. Okay. So here's theorem 3. Extreme values on a closed interval. Okay? Not talking critical points now, extreme values. It's sort of going back and forth. I really don't care for their organization or lack of organization, but make it make sense to them. Assume that f of x is continuous. That's a good thing to have. On some closed interval a to b. Now, how we started this before, lost the spring out of the pen, it looks like. So the f is continuous on a closed interval a to b. Before we said if that's the case, it's going to have extreme values. Okay, absolute minimum, maximum, maximum. Okay. Now, let f of c be the minimum or maximum value on a to b. Okay? Be the minimum or maximum value on a to b. Now, they don't say whether c is allowed to be a or b. They don't say it. It just says that c is somewhere in the interval, and it could either be a or b or anything in between. So f of c, let that be the maximum, minimum, or maximum value on AB. Then C is either a critical point or it's got to be one of the endpoints. Okay? So, if that's a minimum or maximum, that could be the endpoints, A or B, but if it's not, then it's going to be a place where it's a local minimum or maximum, and that then will make it a critical point. Okay? So C is either a critical point if it's interior or it's one of the endpoints, A or B. Okay? So there's the third theorem.
So on that problem that we were doing earlier with the 3 would be an endpoint?
Which one was that?
When it was like x cubed minus 9x squared plus
Right, this one right here.
Yeah. So that 3 would be an endpoint
Where was it? 3?
on the outside.
Oh, no. That 3 is a factor. X is not related to 3 at all. Okay. Because you see, that's what I was saying before. If you set X equal 3, then this would be a plus 1, this would be a minus 1, and then you would say that minus 3 was equal to 0, and that's just not true. Okay? So no, that 3 is not. It's only factors that contain the variable that will produce the critical point. If the factor does not contain a variable, you divide it out. Okay? Yeah. Okay. I remember now. Okay. We already done that one. Okay. All right. Now, let's go back to Theorem 3 for just a moment here. There's a little note on the margin. It says, in this section, we restrict our attention to closed intervals because in this case, extreme values are guaranteed to exist, as Theorem 1. Optimization on open intervals is discussed in 4.7. So we'll get to that later. Okay? So, I think this is part of example 3. We'll ignore this for a while and go on and do 3. Find the extrema. This isn't the same one we no. Okay. Find the extrema, which are the plural extreme values of f of x equal to 2x cubed minus 15x squared plus 24x plus 7 on 0 to 6. Okay? It says find the extreme values of that. Okay? Now, how would you approach that? Okay, excellent first choice. Let's take a derivative. F prime of x is going to equal 6x squared minus 30x plus 24. Okay? You took a derivative. What do you do with it? Okay. Yeah, I would definitely do that. But before you factor it out, what are we interested in that derivative being? Okay. We're going to do that. We're interested in where that derivative is either 0 or doesn't exist. Well, that's a polynomial that's going to exist everywhere. So we will rule out that doesn't exist. So we're interested in whether it's 0. So then we set it equal to 0. Now's a good time to factor. And factor out that 6. And that doesn't enter the picture anymore at all, just like that 3 did. Okay? What do you have left? X squared 5x plus 4 equals 0. I can divide out the 6. Done. Gone. That still equals 0. Okay? So let's just deal with this. X. Okay? X times x. What signs would they need to be? Both negative, because the product is positive, so that means they have to be the same. The middle one's negative, so they both got to be negative. 1 and 4, exactly. And what does that give you? X equal 1 or x equal 4. Those are your two x values for your critical points. That's what we're finding. Now, we also had places where the derivative doesn't exist, but it exists everywhere. So we rule those out. But remember what we're looking for here are extreme values. Find the extrema here. Your extreme values can also be at your endpoints. So we have 4 values to check. X equals 0, x equals 1, x equals 4, and x equals 6. Now, if one of these had come out to be a -2 or a +7, you rule those out because they're not on the interval. Okay? But these are both inside the interval, and you have the endpoints. So what we have to do now is go back to the original function and evaluate each of those. The f of 0 is really easy to evaluate. What is it? 7. Okay, there we have a value. Then let's do f of 1. That's going to be not too bad to do. What would it be? It's just going to be add your coefficients, right? Okay, so that'll be 2 minus 15 plus 24 plus 7. Okay, now you have 3 positives there. 24 plus 9 would be 33, minus 15 would be 18, I think. Okay? I think we can rule out f of 0 being a maximum. Okay? Can't we? Okay? Because f of 1 is greater. We can rule out 1 being the minimum. Okay? Let's go on to the next one. Alpha 4. Woo! What would this be? What would this be? 2 times 4 cubed minus 15 times 4 squared plus 24 times 4 plus 7. Okay? That would equal 2 times 64. Is that right? Is 128. Minus 2 squared is 16 times 15. Oh my word. 16 times 15. Okay. Is what? 240. Thank you. Plus, and that's 24 times 4 would be 96 plus 7. Okay, let's add our positives together. That gives you a, well, let's add 96 and 7. That gives you 103, right? Plus 128 would be 231. And 231 from that would be a minus 9. Okay, so it looks like alpha 4 could maybe be a minimum. Alpha 0 is out of there. Okay, 0 is not going to be an extreme value. Could be 1, could be a maximum, 4 could be a minimum, but we've got to consider one more point, and that's your other endpoint, 6. F of 6. Oh my. Let's just do this one with a calculator as you go. 2 times 6 cubed minus 15 times 36 plus 24 times 6 plus 7. $43. Okay. We already ruled out 0 being an extreme value. Now we can rule out 1 being an extreme value. Our absolute minimum on that interval is -9. That's going to be at F = 4. And our absolute maximum is going to be at the other endpoint, x = 6. And that would be 43. So what does that tell us? Don't know if it tells us a lot. Looks like the function's increasing from 0 to 0 to 1. And it's it's decreasing from 0 to 1, increasing 0 to 1, decreasing from 1 to 4, and then increases big time between 4 and 6. Okay? The 1 and 4 are places where you have horizontal tangents. The tangent is 0 there. And it seems to be going up past 1 because it's 0 at 1. Down. The horizontal tangent at 18 and 0 at 7. So it's decreasing there, reaches a local minimum at 18, then goes down to absolute minimum at -9, and then goes up to your absolute maximum at 6 on that interval. Okay. Min and max, got it. Now they do the zeros first and then do the critical points first and endpoints later. I don't care how you do it. You can do it any order you want to. Okay. So let's do example 4. I think we've got time. Well, let's see. Before I do that. Here's the function. Okay, sorry about that. I didn't realize they had the graph of it on the slide set. Here was our function that we just did. We knew it started low here, went to local maximum here. Okay, went down to a local minimum here that for this interval it happened to be the absolute minimum, and then it went to our local maximum there. Now, of course, they compressed the y scale and expanded the x scale so you can see it better. Because huge values on y, relatively small changes on x. Okay. So there's what I was trying to describe to you. I wish I'd have just gone to here. Okay. This, I believe, is going to be example 4. Find the minimum of this one. F of x is equal to 1 minus x minus 1 to the 2/3 power. On the interval, -1 to 2. Remember, these have to be closed intervals for us to use the definitions we're doing. What would you do first? Find the derivatives. Good first answer. Like I was told, I hope you don't get offended by this, but it's sort of like in children's church, and whoever's leading that, whatever question they ask, some kid usually says Jesus. Okay, and that's usually a good answer, right? So when you're in this, Calculus 1, first question, what do you do first? first guess would be take a derivative, okay? Not quite equivalent to Jesus, but, fairly, okay. So let's take a derivative. F prime of x would be what? Okay, only a minus 2/3 times x minus 1 to the two-thirds minus 1 would be negative 1/3. Okay? Now, I'm going to write that, even though taking derivative, I love to have it in exponential form. Okay? That's the only way I do derivatives. But to see what it looks like, I'm going to write it in another form. This will be a minus 2/3, but then also in the denominator is this, the cube root of x minus 1. Isn't that what that means? Okay. Now, do you think that's ever going to be 0? Never. Because for this to be 0, the numerator would have to be 0, and minus 2 is never 0. 2 is never 0. So this is never going to have 0 as a derivative. But looking at this, you might also have a problem. And what's that? Your denominator could be 0. If x is equal to 1, you have a 0 in the denominator. You can't have that, can you? So that means your derivative doesn't exist when x equals 1. Now remember the two places where your critical points were? Where the first derivative was 0, doesn't happen in this problem, or where the first derivative doesn't exist. That does happen in this problem, and it happens at x equals 1. So that's the place that are critical point. So we consider 3 different points here. Our endpoint, x equals minus 1, your critical point, x equals 1, and your endpoint, x equals 2. So let's find out what the function is at these 3 values. F of 1 would be what? Minus 1. It would be 1 minus, say that again. Negative 1 minus 1 is negative 2 to the 2/3 power. Whatever that is, okay? I would say pull out your calculator and do, you know how to do fractional radicals or exponents on the calculator. Not hard. Negative 0.5874. That's going to be close enough. Okay, let's do f of 1. F of 1 would be 1 minus, and 1 minus 1 is 0. So 1 minus 0, that's just going to be 1. F of 1 is going to be 1. Okay? We could have a local absolute minimum. We could have an absolute maximum. But let's see what f of 2 is going to yield us. 1 minus zero. No. 1. 1 minus 1 to the 2/3 power. And that's going to be equal to 0. Right? Okay. So guess what? That right-hand end is not going to be a max or a min. The left-hand endpoint is going to be our our absolute minimum, and our x equals 1, that's going to be our absolute maximum. And here's the picture of it. This is negative 0.5, a little more than 0.5, that looks reasonable. Here it goes up to 1 here, and here it comes down to 0 there. So sure enough, this is neither a max or a min, that's your max, that's your min. Okay? Those are your extreme values. You consider the endpoints and the place where either the first derivative is 0 or the first derivative doesn't exist. Okay? I think we've run out of, no, wait. Yeah, we have. I keep forgetting. I have one calculus class that ends at a 40 and one that ends at a 10. This one ends at 10. Okay, so we'll start next time, if I can find my pencil, on example 5. Okay? And homework exercises. We almost finished 4.2, not quite. Homework exercises here. I think you can do 1. You can do any of the odds 3 through 19. Okay? And by the way, on that page 206 there's a picture of Pierre de Fermat that did Fermat's theorem that we did. And a friend of his, Rene Descartes. So you could actually do your paper on either of those. Okay? And then if you read that, you'll see there's also Newton and Leibniz are both mentioned. So there's a lot of possibilities there, or you could write on any of the things. Okay. Anyway, through 19. Then I would say you could do either 21, 23. I'll say any of the odds 21 through 27, though they say you might need a computer-assisted system, algebra system for 27, and you might need a graphing utility for 25. If you have either, go for them. And then let's see, I think you can do any of the odds 29 through, 57. Okay, I think that looks like maybe a good place to stop. Yeah, let's stop there and we'll pick up the rest of those next time. All right, good deal. Sorry that I was so out of it today, but I made it through the class, so I'm halfway through.